Hi and welcome to this webinar. My name is Christian Armstrong and my project has been gratefully awarded Teledyne's RESON SeaBat T50-R, a multi-beam echo sounder sonar. As part of my PhD research interested in the seabed's physical stability, this equipment is expected to be rather paramount in collecting some really interesting data. The project is affiliated with the University of the Highlands and Islands, or UHI, hosted by the Scottish Association for Marine Science, or SAMS. And this is said rather picturesque university. UHI is Scotland's newest university and is comprised of 13 individual institutions scattered in some of the most remote areas of the Scottish Highlands. The Oban campus UHI, where I'm based, hosts but one degree, marine science, but does so really successfully, being rated second in Scotland and sixth in the UK for degree quality. Many of the UHI institutes are partnered with an organisation that sort of facilitates the education. So what better partnership for a marine science degree than the Scottish Association for Marine Science? Whereas UHI is Scotland's newest university, SAMS is Scotland's oldest independent marine science institute. With around 150 staff, the SAMS UHI campus can host 160 students, both undergrad and postgraduate, providing direct access to the cutting-edge marine research undertaken in Scotland. There are three main sort of key focus areas for research, namely dynamic coasts, blue economy, and ocean systems. Now, dynamic coasts focuses on the natural marine systems and the consequential human interaction with the coastal seas. Blue economy is interested in our sort of sea-derived economy, focusing on sustainability first and foremost. And ocean systems looks at global oceanic processes like ocean circulation, for example. My research takes place within the dynamic coasts. So SAMS would be very little without the amazing people that work there. Similarly, I couldn't do this research project without a fantastic team guiding and supporting me. For the sake of these 10 minutes, I cannot mention all, but some special thanks to my project supervisor, Dr. John Howe, my secondary supervisors, Dr. Christopher Allen and Dr. Richard Bates, my industry advisor, Peter Watson, and some special thanks to the project's technical support from the likes of Colin Abernethy, boat skippers and support, Sarah Reed, Norman Smith, and the physical oceanography support from Dr. Andrew Dale. So this is what we have been awarded, a RESON SeaBat T50-R. Now, SAMS is actually a host of some Teledyne equipment already, and so there is a wealth of expertise with respect to deployment of the equipment, processing and analyzing the data collected. So not only do we have the glider you saw on the last slide, the Teledyne Gavia autonomous underwater vehicle, or AUV, but we also have a 2005 RESON SeaBat 7125 multibeam sonar that has been used extensively for research in the past. However, by having access to this brand new RESON SeaBat, there's an opportunity here to not only collect world-class bathymetric data, but also to assess the advancements of Teledyne technology over the past sort of 15 years. Together with SAM's research vessel, the Shomar pictured here, we hope to shed a light on not only poorly understood bathymetry, but also on the technological advancements of Teledyne. So what are we going to apply this to? Well, here we have one of the two sites of the so-called poorly understood bathymetry, the Gulf of Corryvreckan, Western Scotland. Now, this tidal channel is home to the world's third largest whirlpool and some of the fastest tidal flows on Earth. As we can see, the glacially over-deepened channel between the islands of Jura and Scarborough features depths in excess of 200 meters. Due to a difference in the water depth or sea surface height either side of the channel, ultimately caused by the tides, and combined with the steep and narrow channel walls, tidal currents through this channel are extremely accelerated. The sound alone of the turbulent water found here can actually be heard up to 10 miles away, and there are several shipping anecdotes that tell stories of being unintentionally sucked through the Gulf of Corryvreckan during voyages if they get too close. So clearly, this is an incredibly inhospitable and dynamic environment which is why little research has really been conducted in this area. A bathymetric survey conducted by SAMS in 2012 using the aforementioned RESON SeaBat 7125 produced this particularly staggering 2-meter resolution bathymetric map. The distribution of glacially scoured bedrock uncovered by the intense hydrodynamics and the massive sediment structures found at the boundaries of the main flow paths indicate an incredibly dynamic seabed environment. It is these sedimentary features, indicated by the 3 black squares numbered 1, 2, and 3, that are of particular interest. So this project looks predominantly at seabed stability, or the potential to change state or appearance. For example, bedrock is relatively stable as the flow of water does little to change the broad appearance of bedrock. By comparison, sediment may be transported by the water flowing around it, and by moving the sediment, structures form like sand dunes in the desert. These structures then migrate and move as a whole mass, which changes the state of the seafloor, ultimately making the region less stable. There are several types of these features, including sand waves, dunes, and ripples, banks, and ridges. The movement of these structures clearly represents a massive amount of sediment transported. The structures found in the Gulf of Corryvreckan, mainly dunes and banks, are of such a scale that the extreme tidal zone results in an extreme amount of sediment transport and extreme instability. Here we see just how accelerated these flow speeds are. The coloured circles represent GPS coordinates of drifters, essentially floating bodies with antennae attached that were deployed in the Gulf, with the colour representing the speed associated with the drifter at that point. The maximum flood tidal speed recorded, as you can see, is 5.93 meters per second, or more than 13 miles per hour, 11.6 knots. Whatever the units, it's really fast, and the contrasting ebb flow speed, albeit slower, is still strikingly quick. Additionally to the Gulf of Corryvreckan, there is a second side of interest. Whereas the Gulf is over 20 miles away as the crow flies from SAMS UHI, the Falls of Lora at the mouth of Loch Etive is less than 1 kilometer. Kind of like squeezing the end of your garden hosepipe. The water is ejected through the Falls of Lora out of Loch Etive when the tide ebbs. The exposed bedrock seen in the image below the Connell Bridge is indicative of the accelerated flow speeds here. However, away from the exposed bedrock, similar sediment structures have been identified as those found in the Gulf, identified within the white boxes here. The locality of the Falls of Lora makes it the ideal place to study the morphological evolution of these structures, and with Teledyne's help, we aim to provide high-frequency repeat surveys of these regions of interest. So here we have an opportunity to really assess firstly the operational advancements of Teledyne technology over 15 years, from the RESON SeaBat 7125 to the new T50-R. With respect to the geophysics, the sedimentary structures identified are found throughout the coastal seas. With increasing interest in offshore work and construction, the stability of the seabed is clearly an important consideration, as a shifting sedimentary structure may damage equipment or materials. In shallower water, the movement of larger dunes can actually render the depths of shipping channels in and out of harbours unreliable if the shifting sediments alter the water depth considerably. As part of the PhD project, I'm really interested in adopting the most efficient and accurate method to quantifying the stability of the seabed. By adopting a method used commonly in fluid dynamics, particle tracking, these vector fields can be generated representing the movement of sediment structures. Clearly, these vector fields show some outliers. However, I've done some recent work that has resolved many of these, and it shows some promisingly accurate results. So the questions really are, when applied to structures such as this so-called trellis dune, where wave interference is actually suggested in the Gulf of Corryvreckan, what will this vector field look like? How will the sediment transport pathways resolve in such a complex sediment transport environment? And lastly, how far has Teledyne technology advanced in the last 15 years? So that's it for the project, and what the team at SAMS UHI and I will be working on. we're all super excited here, and if you want any more information on anything I've presented today, I'd be glad to take any questions by email. Alternatively, you can follow the project on Twitter @CarmSeas. If you're interested by the research at SAMS or the education of UHI, you can find out more on the web pages that I will leave here. Lastly, thank you very much for listening and for Teledyne awarding us this equipment grant. We cannot wait to show you what we find. Thanks and goodbye for now.